Yeah, that's a good point, Emiliana. All right, so at the heart of any like optimization problem, once you come up with the picture and the equation, it just turns into finding an absolute max or min of a function on an interval. All right, so to find the absolute min or max of we're going to start off with just these absolute min max problems because those are sort of like at the basis of what any optimization problem is. All right. So remember the idea here was to find the critical points and then test the function at the critical points and at the endpoints. All right, so we find critical points by taking a derivative and then seeing where the derivative is either 0 or undefined. All right, so let's take a derivative of f. So what's the derivative of 2x cubed? Thank you, thank you. So indeed, the derivative of 2x cubed is 6x squared, and you're all experts on this by now, I'm sure. The derivative of 15x squared is 30x, and the derivative of 24x is 24. Okay, and we want to set this equal to 0. All right, so with a quadratic, the first thing you want to do is to try to factor it. So what can I, so don't forget the 24 from the 24x. So what can I factor out of this polynomial? Good. I don't know what any of those words mean. All right, so if I factor out 6, then I'm left with x squared minus 5x plus 4, and this hopefully we can just factor into two linear terms. To add up to 4, or to multiply to 4, they either need to both be positive or both be negative. All right, and they need to add up to 5. So we end up with x minus 4 and x minus 1. All right, so so we have the critical points. So now we just need to test the function at the endpoints and the critical points. So I'm going to change colors arbitrarily to keep your attention. And let's see. So the endpoints are 0 and 5. And the critical points are 1 and 4. Okay, and we just plug these into the original function. All right. So if I plug 0, and remember, you plug these into to f, not f prime, right? If you plug in 1 and 4 into f prime, you're just going to get 0, because that's how we found 1 and 4, right? If I plug 0 into the original function f, what do I get? Good. And if I plug 1 in, what will I get? Good. So you'll get 2 minus 15 plus 24, which is just 11. Let's see. If you plug in 4, you'll get negative 16. And if I plug in 5, you get negative 5. Just some quick mental math. All right. So what's the max? $11. And the min? Negative 16. So pay attention to the wording of the question. If you're asked like what is the max, that's the y value. If you're asked like where does the max occur, that's the x coordinate. All right. So the maximum value the function takes on this interval is 11, and that happens at 1. The minimum value the function takes you could graph it, but that's not really what we want you to do. I don't know if you could quickly graph a cubic like this in any case. All right, so I want you all to look at the next couple. All right, so we'll spend, say, 6 minutes. I'll split you on or maybe just do the next one. All right, so take 5 minutes to do that one, and I'll split you all into groups. Okay, so let's look at this. So this one's actually not too bad, really. So if we take the derivative of g, we get e to the x minus 2. We set it equal to 0. E to the x equals 2, which means that x equals the natural log of 2. All right, so we have the natural log of 2 as our one critical point, and we just test the function at 0, ln of 2, and 2. All right, so if I plug 0 into the function, I get e to the 0 minus 0, which is just 1. If I plug in the natural log of 2, I get e to the ln 2 minus 2 ln 2, which is 2 minus 2 ln 2. All right, and if I plug in, it is 2x, hence the 2 times ln 2. Okay, if I plug in 2, I get e squared minus 4. Yeah, in order to compare these. So you would kind of like need to have a calculator in here. So this would be, this number is less than 1, and this number is greater than 2. So this is your min, and this is your max. Yeah, I plug 2 back in, so I get into f of x. So 2e to the second power minus 2 times 2. Yeah, just this is why like you just be clear on like what you're saying. Like so use sentences to say like you could say the maximum value the function takes is e squared minus 4, and this occurs when x equals 2. Word's good. All right, in the interest of time, I'm going to skip this next one because, I mean, all these problems are basically the same thing. They have the same process, and I want to move on to the actual optimization problems. All right, so consider a rectangular piece of cardboard with dimensions 5 by 8 feet. Squares of side length x are cut from each corner of the rectangle, and the resulting piece of cardboard is folded up into a box with no lid. What are the dimensions of the largest such box? So it means largest means we're maximizing the volume. All right. Okay, so we cut squares out of each of the corners. Yeah, right. This belongs in the Louvre. So the dimensions of the box are 5 by 8. And we cut squares out of each of the corners, so you could say that these are like, these sides have length x and x. Okay, so when I fold up, so volume is length times width times height. All right, when I fold these pieces up, like the height of the box if it was resting on the ground would be x. Okay, what would be like the width and length? So what would be good, so 5 minus 2x and 8 minus 2x, exactly. It says, what are the dimensions of the largest such box? No. All right, so you're talking about what is the largest three-dimensional object? Yeah. You're generally talking about the volume. All right, so now we have an equation for volume, and we will optimize it. The first thing we want to do, or what we want to do next, is maybe look at the domain. Okay, so the smallest value x could be is 0. All right, so the domain, like sometimes whether you use open or closed brackets, you need to like just justify what you're saying. So I'm going to use open brackets because, for example, like for one, x is our variable. So we're talking about what are the values x can be. All right, I'm going to say I use an open bracket around 0 because if x is 0, then the volume is 0. So that's clearly not like the largest box. All right, what is the biggest value that x could potentially take, or like up to? Good, 2.5, yeah. Because if x is 2.5, then on the like length 5 side, the rectangle, like the squares will eliminate that whole side basically when I cut them out if x is 2.5. Okay, so it'll go up to 2.5 or 5 over 2. Okay, and the same thing, like I'm using an open parentheses because if it was 2.5, there would be no box. Like there's no, I would cut out so much stuff that there's no box. By taking 5 divided by 2. Okay, so think like, we break out another color here. All right, if x was 2.5, so if like x was 2.5, then I would be cutting out this square and this square, and there'd be no box, right? I'm cutting out too much of it. There's nothing to fold up then on that side. All right, so let's do this. So we just need to basically FOIL this out. So this is the same thing as x times 2x minus 5, 2x minus 8, where I factored out a negative from both of those other factors, and the two negatives cancel out. So let's see. If I distribute this x, I get not 2, 2x squared minus 5x times 2x minus 8, which gives me 4x cubed minus 16x squared. Minus 10x plus 40x. If I distribute the x to the 2, I multiply x by 2x minus 5. Yeah, so that's like if I cut out, so imagine that like I cut out squares that have 2.5. Yeah, the last term is 40. All right, that have side length 2.5. 2.5 is half of 5. So if I cut out like this square with side length 2.5 and this square with side length 2.5, it'll eliminate the entire like side, that entire side. So I wouldn't have a box at all. Yes, thank you. It would be minus 10x squared. Okay, so we get 4x cubed minus 26x squared plus 40x. You only distribute the x once. There's only one x. So once I multiply it by the 2x minus 5, I don't distribute it to the other term. If that's what you mean. Unless I'm missing something here. Yeah. Okay, so this is our volume function, and now we'll take the derivative. So this will be 12x squared minus 52x plus 40. All right, we can set this equal to 0. All right, you can factor out a 4, and then let's see, you'll get 3x squared minus 13. Okay, and then I wonder if this factors. I think so. Negative 10. Yep, so we get, this gives us x equals 1 and x equals 10/3 as critical points. All right, so since our domain is open, we don't need to test the endpoints. And if you plug those in, you would just get 0. So I really only need to test x at 1 and 10/3. Since this is a cubic, since my original function was a cubic, one of these will be a max, and one of them will be a min. So you could, I guess you could plug these in, or you could do a sign chart to determine which one's a max and which one's a min. So let's do that. So I'm only going up to 0 and 5/2. Although actually 10/3 is outside of the domain, isn't it? Yeah, exactly. Good point. So 10 over 3 is outside of the domain, so we only need to look at 1. Okay, and if I plug in something between 0 and 1, what is 1? Into V prime, that is. If I plug in something between, what? If I plug in something between 0 and 1, I'll get a negative times a negative, which means the overall sign is positive. And if I plug in something to the right of 1, I'll get a negative and a positive, which means the overall sign is negative. Okay, so my function goes from increasing to decreasing. All right, so 1 is a local max, and that's basically our answer when x is 1. All right, so it says what are the dimensions? So we have x is 1, and then the other two sides are 5 minus 2x and 8 minus 2x. So 5 minus 2x will be 3. 8 minus 2x will be 6. So 1, 3, and 6 are the dimensions of the box. All right, so let's see. So which one do y'all want to do first? Question 3 or question 4? Oh wait, let me do a poll. Three's running away with it. Just to make it easier, so I flipped both of them. Basically what I did was I factored out a negative from each of them, and since I factor out two negatives that cancel, I just prefer to deal with positive coefficients. All right, in a landslide victory, 3 takes it. Okay, so the slant radius of a cone is the distance from the vertex to the edge of the base. Among all cones with slant radius 4, find which has maximum volume. All right, so what this means, if you have a cone, it's basically saying that like this length, like the length from the top of the cone to the side is 4. That's the slant radius. Okay, the other dimensions we can look at are the height, and the radius of the circle, that's the base of the cone. Okay, so I need something, and the volume we're given, the volume of a cone is 1/3 pi r squared h. Okay, so I want to take a derivative, but at first I need to I need to relate H and R. All right, I need to come up with some equation that relates H and R. So think about that red triangle. What equation uses H, R, and then the given value 4? It's named after a Greek cult. Close. Yes, Pythagorean. The Pythagorean theorem says that H squared plus R squared equals 4 squared. All right, so I would probably solve for R squared, since R squared is already like a point on the there's already a term in the volume function. So R squared equals 16 minus H squared. It is a Greek cult, yes. Or it was. All right. So then we just replace R squared with 16 minus H squared. So we get the volume is 1/3 pi 16 minus H squared times H. Okay, and we can just distribute everything. And we get, let's see, 16 over 3 pi H minus pi over 3 H cubed. Triangles were a pretty radical technology back then, so. All right. Okay, so this is our volume function, and we can just take the derivative. So it's now a function of H. Of course, I would never lie. All right. So this is just a polynomial in H. All right. So you just take the derivative using the power rule and set it equal to 0. And you get pi H squared equals 16 pi over 3. So H squared equals 16 over 3, or H equals 4 over root 3. Okay, so if H is 4 over root 3, then the radius is given by R squared equals 16 minus H squared, and H squared is 16 over 3. Okay, and then you would want to use a sign chart to determine that this is actually a local max. So I guess we need to talk about the domain here as well. So this is a question where there's not really any restriction other than the slant radius is 4. So depending on what, like basically as H varies, R could vary as well to accommodate any positive number. H can be any number bigger than 0, and yeah, H could be any number bigger than 0 essentially. If H is really, really, Or sorry, no, h can't be bigger than 4, actually. Never mind. JK. Because if h is bigger than 4, then that can't have a slant radius of 4. Okay. So and you would want to use a sign chart. Right, it can't be equal to 4. Yeah, exactly. Yeah, yeah. Okay. All right. So now let's look at the last question, which involves linear approximation. So for each function and point A below, write down the linear approximation L of x to the function at A, and then use it to estimate the indicated value. So remember, this is really just finding the equation of the tangent line to the curve at the given point, and then you just like plug in 7.5. All right. So L of x is just f of A plus f prime of A times x minus a. And this is just the equation of the tangent line. All right, so for this first problem, if we want to approximate sine of 0.75, we'll use sine of x and the value pi over 4. So f of x is sine of x, and a is pi over 4. All right. So what do I need? I need to know what f of a is and what f prime of a is. All right. So f of a is sine, means we're looking at sine of pi over 4. All right. So what is sine of pi over 4? Good. Okay, I also need to take the derivative of f. So what's the derivative of sine? Good, cosine. And then I need to evaluate it at a. So I need to know what is f prime of pi over 4, or cosine of pi over 4. And this is just root 2 over 2 as well, right? Good, good. Okay, so now we can just plug all this into our linear approximation function. So the linear approximation will be f of a, which is sine of pi over 4, so root 2 over 2, plus f prime of a, which ends up being cosine of pi over 4, or root 2 over 2, times x minus pi over 4. Okay, so if we want to approximate sine of 7.75, we're just going to plug in 0.75. Yeah, so on the module problem, we do have you do sort of like this a few times, and we do ask you to use a calculator. So we sort of like ask you to use a calculator at certain points in the module problem. Okay, so then for at least on the essay part, like on the online part, a lot of times you might leave something like this. Yep, indeed. Okay. Um, all right, so for the next one, we're using the natural log x at 1 to approximate ln of 1.05. So we basically find, so first let's just find the derivative. So what is the derivative of the natural log of x? Good. And then since a is 1, we plug 1 into the function and its derivative, right? So ln of 1 is what? Good. And f prime of 1 is 1 divided by 1, or just 1? Okay, so L of x is f of a, which in this case is just 0, plus f prime of a, which in this case is just 1, times x minus a, so x minus 1. So our linear approximation to the natural log function is just x minus 1. So then ln of 1.05 is estimated by plugging in 1.05 into our approximation, which just gives us 1.05 minus 1. Or 0.05. Okay. So I will post this indeed just in time. I will post this to Blackboard in a second. Amy wishes you good fortune in the module to come while she bathes herself. Hey, look at me. She says it's very important to manage your hygiene in coronavirus times. Amy. Okay.